Hello everyone. Welcome to another problem session. This time we're going to revisit the collision problem uh, in reverse. So instead of these guys coming to collide and then becoming one, we're going to do this composite particle breaking up into two. Okay, so you can think of it when they break it up, two possibilities in a sense. This is included here, but we'll do one and two separately. Okay, two is of course more complicated. So one, looking at one, they just go along the x-axis, and you may want to figure out, what are these ratios of these speeds and things like that. Okay. Over here, you can do it in a lab frame. This whole thing is a lab frame over here. This is lab frame. Or you can think of the same thing in a center mass frame. So we are doing this because this is one of the problems, a classic problem that we kind of didn't do before we did the four vectors. Pretty soon we're gonna get to the four vectors, and I'm gonna use four vector notation just to get a more practice with it. You don't need that here, but let's do this calculation and a couple of steps. So let's do what we'll do like a non-relativistic, just as a practice. So suppose I do in the lab frame, and you will see I'm going to do both lab and the center mass for the non-relativistic. And I'm going to do one first, just do one. So in the lab frame, you have energy conservation and momentum conservation, right? So what I'm going to get, I'm going to get for the energy conservation, I'm going to get energy here equals energy here. So it's going to be half m1 v1 square plus half m2 v2 square equals to the energy here. So it's going to be half mu square plus binding energy. So this is so there's a whole bunch of knowns here. You can see this is a known. Maybe this is given, maybe the masses are given. And so there are like three unknowns here. So this is a known and this unknown. So we need more information. So second information that I can write is in here, momentum conservation is going to be just one line. So this is going to be m1 v1 minus the way I've written down. So this is, I'm writing x component. So this minus v1 is the speed plus m2 v2, and this x component will be mu. So right now we have this is unknown and this is unknown. So if we don't know the binding energy, then we don't have enough information. There's a slew of answers here. So this is the case with almost all these cases. We are going to have some free parameters in a sense. So if you solve this, you need this to solve it. So let's see. I'm just going to call E for the entire thing. I'm just call it E, and say this is somehow it was known to me. Okay, so if clearly I can now solve it, and you can just plug in and so solve for v1 v2 given E binding m and u. Okay, So that's the lab frame. Let's do the same thing in the CM frame. The CM frame, what will we get? CM frame is, and we are in the non-relativistic. So, you know, the speed. So everything here in non-relativistic, this v1, v in the, let's call all of them uses 0 as a subscript to denote quantity here. So v in any of this speed in vector form plus u is u I hat u, that should be the velocity that's over the lab, in the lab. Let's call this c. In the CM frame, lab frame will be a little like this, right? Because if this was 0, they will be the same. If u equals v lab, v with respect to lab, so like something like this is in the lab is going u and this is going u. So this is going to be same, right? So this will be a relationship. Okay, so that's the relationship between the two in the non-relativistic, Okay, so if you want to convert from one to the other like this, but regardless of converting, we don't want to convert, we're just going to do it over here. So in terms of energy conservation, so we have at rest, and then we have this. So we have a half m1 v10 square plus half m2 v20 square equals to 0 plus binding energy. So you just need binding energy here. And for momentum is 0 here, so it's going to be same here. So m1 v10 will be m2 v20. So right away we can see quite a simplification because of this here, and we can, not quite a bit, that's kind of overstating it, because we are just in one dimension. It's really not much of a simplification, I should say. Now if I do the same kind of thing for this, and we will see, let's see what happens if I'm in two situation. So if I'm the lab and I want to do situation in two. Okay, when I'm in the lab and I'm doing a situation, this situation, two-dimensional situation, now we have a really nasty thing going on, right? We are going to have kinetic energy. The first one remains the same. This one remains the same, because there's no vector nature here, just speeds and everything, right? And in terms of we have an equation along the x and along the y. So along the x is along the x we have a m1 v1 cosine theta 1 plus m2 v2 cosine theta 2. So that's the left side. Already you can see cosine theta 1, cosine theta 2, which is getting nasty, okay? And the other side is just mu. And the y direction is m1 v1 sine theta 1 plus m2 v2 sine theta 2. The way it's written, the way the angle is defined, that's equal to 0. So now we actually introduce a whole bunch of, so we have unknowns, EB, M, U. So it's the same unknowns as before, V1, V2, and then we have introduced theta 1, theta 2. And you can see that I just have 3 equations and we have a whole bunch of unknowns, right? So even if we just give this as before, and that actually solved the problem before, now we have we have a freedom here. So we can only solve 3 out of these 4 quantities. From here, if I gave you these guys, you can solve the remaining 2. But there's 2 more things come in here, and so it's a little complicated algebra you have to do, but you'll end up with solving everything in terms of one of them. Okay. How about if I do 2? I do in the CM. What do I get? Let's see. Let's do 2, but do in CM, and it's still non-relativistic. Okay. We'll do relativistic in just a moment. So let me pause it. I'm just going to write it out, and then you can look at it. Okay. Okay. So energy equation again is the same, but something interesting happens. If we look at momentum is 0 here. So to the momentum x, momentum y in here, momentum x and momentum y. So if I look at momentum x and momentum y, then I can actually get this equation. So momentum x would be m1, and this is v10 cosine theta 10. This angle is not the same as that angle. Okay. Should be plus, and this is v2, so we can add the plus m2 v20 cosine theta 20 must come out 0. That's the x, and the y will be m1 v10 sine theta 10 plus m2 v20 sine theta 20 equal to 0. And if I look along this, you can see m1 v10 must be equal to m2 v20 on the other side, right? So all of these guys, you can say this cancel out, this can take them out, and from this what I get is simply theta 10 has to be equal to, looking at this diagram, they're going to have to be in the same line, so pi minus theta 20. So there's only one angle, so you don't have to solve for 2 different angles. So in here, let's look at list of unknowns. So list of unknowns is going to be E binding energy, V1, V2, and only one of them theta, let's call it theta 0. There's only one theta 0. And from here, if the masses were equal, if the masses were given, then if we know one, you can know other. This is 0, 0. So you don't need both of them. If the masses were known, then you only need one of them. And we have one equation, and we got all these unknowns here, right? So we have unknown this, unknown this, unknown this. Okay. So there is a freedom here also. There was a freedom here in terms of number of equations, and this is the same way. You just have energy equation to work with, and this freedom will carry over in the relativistic. Okay. So when you work out relativistic, we want to work out relationship between energies and angles, or momentum and angle, when we work out the 2-dimensional case. All right. Just like in 1-dimensional case, we want to work out a relationship between these speeds and the incoming energy, for instance. All right. So similarly, we're going to have that same kind of flexibility of freedom when we are dealing with a relativistic situation. Of course, non-relativistic situation like this is, almost like a prerequisite for you to be able to do it. So let's look at now the whole thing relativistically. Okay. So when we're doing relativistic calculation, we really don't go out into half mv square, things like that. So in the relativistic calculation, we have a, I'm going to set speed of light equals to 1 for the formula to become simpler. And so using that in c equals to 1, then in any frame, you have a energy square equals to p square plus rest mass square. I mean, this if c was not 1, this comes from e square equals to p square c square plus m0 square c to the power 4. So setting c equals to 1, and later on I can put the c back in. But it's really, this one is too much writing, so I'm not going to write that. So that's one of the important relations. It's any frame. So you can see that in another frame is p prime square plus m0 square. So I can see that this is same. So prime will be used for two different frames. So e square minus p square in one frame. So let this be left frame, and this is c frame, and some speed u. So this, everything here make it prime and everything unprimed. So this will just be e prime square minus p prime square. So this is really very important relation for us. Or you might say e square minus e prime square equals to p square minus p prime square. Same relationship. So you remember this. You really need to be able to use it whenever necessary. So another equation that's necessary for you to remember is E times the speed of the particle is equal to P. And you can see, how do you see that? You say P equals to gamma m0 v. And gamma is the gamma using the v, this speed v. And E is gamma v m0 c square. So this is putting the c back in. So take a ratio of these two. P over E is going to be v over c square. So P equals to v over c square E. And when c is 1, it's just VE. It's like that. So these two equations, I think very useful. You should remember them. And let me pause and clean this up so that I'll have more space to write. Okay, so let's set up those equations I will get. So I will get one equation will be energy conservation. So right, energy is, you have a energy of the whole thing. Of course, this will be equal to gamma u mc squared. That's what that will be. And so energy of the other particle E1, and this will be gamma v1 m1 c square. And c is equal to 1, so I don't need that. Plus E2, and this will be gamma v2 m2. Now already see these gammas are, if you remember, gamma of something is 1 over the square root of 1 minus u square over c square, and I just set c equal to 1. So it's going to be like this. And this is going to be with v. Gamma v1 will be 1 over square root of 1 minus v1 squared, the speed which you don't know, and it's sitting down here. It's pretty nasty looking, right? So we should try to always make it so it's very simple. And you will see that over here, it's got some momentum. P equals to momentum of this, P1 plus P2. And if you look at the x component only, this is not 0. Because this is not 0, this leads to a nasty calculation when you start to try to find the relationship of energy and speeds. Okay, contrast that contrast that with doing the calculation using that. So this is in the CM frame. So now the energy is not that, it's at rest. So it's just M, which is like mc square, and C is gamma equals to 1, so mc is, so now this just M, and then you have a E1, let's call it 0 here, just distinguish, this is not the same as that. Is in this frame, what's this energy here, plus energy of this particle. That's is quite, now if you were to say what is this equal to, this is going to be gamma of V10, which we don't know, M1, and this will be gamma of V20, M2. So this guy has a like gamma of V10 is 1 over square root of 1 minus V10 square. Okay, so I hope it's still nasty, but it's less nasty than over there. Okay, then momentum here is the boon. I start with 0, so that's equal to P1 plus P2. And right here, already I get a P1 equals to minus P2. And by design, so this is, what are the magnitude of P1 is, let's call it zeros, 0, 0, 0, 0. So in this frame, and then I can really use these guys to square it. P10 square equals to P20 square, and of course we can just use one symbol, P0, right? So if I want to use momentum in some formula, just one momentum value. Okay, so now P10 square, and I just substitute over there. So that's E10 square minus M1 square equals to E20 square minus M2 square. And I bring this on the other side. So bring this on the other side. It's very simple to do. E10 square minus E20 square equals to M1 square minus M2 square. And then I can use this to actually call it E10 minus E20 equals to M1 square minus M2 square over M. So you have a 1, and let's call this 2. From these two equations, I can add and subtract and already solve this. E10 is equal to 1 over 2 M, add them up, right? Like so, I'll have a M plus M1 square minus M2 square. And E20 equals to M square minus M1 square plus M2 square over M. So now we got the energies, and from these energies we can clearly P1 and P. So P10 will just obtain from right over here. So P10 will be just E10 square over E10 square minus M1 square. And if take a ratio of these two guys, so from there I can get V10 is just going to be P10 over E10, right? P10 over E10. So we got similarly you can do with the second one, but you can see I already solved all the problem here in the CM frame. And how do I get back to my lab frame? Well, I just do the transformation. Rather than do this calculation over here, I do calculation over here and I transform over there back. Let me show you the transformation equations. Okay, so I just summarized it here. So we just only need one of the P0 because they're equal. Both of them have the same momentum. But I need P10x. That will be, I'll take a square root of this guy and I'll get a minus P0. Take a positive square root. And so P0 will be half, like that. And P20x, based on this diagram, is going to be plus P0. Okay, so we're just looking at one dimension. Okay, so how do I get back to getting back to lab? Well, when c equals to 1 and you have this u and then is this the lab, the transformation is the lab quantity E, and these guys will be all primes. I'm going to use primes. E equals to gamma E prime plus U Px prime, and then Px will simply be gamma E prime U Px prime U E prime, and then Py equals to Py prime and Pz equals to Pz prime, right? That's because when c equals to 1, E and P, they are a 4 vector, and all 4 vectors transform like this, right? So these are 4 vectors. We can say Pi, and this is so-called contravariant 4 vectors. So this is denoted as E, P, and then there is another called covariant with the index with down, and we write E minus P for that. And I goes from 0, 1, 2, 3. So this is P0, and this one is P1, P2, P3. Okay, so that's a 4 vector for you, and so all of them have same transformation. So c equals to 1 actually helps out a lot. So from here we just say I want to get E1. Well, from E10 and P10x, so I get 1. So from here I get E1 that I want. I already know the E10. So this will be gamma using the speed with which these things are. So gamma of u, not other gammas, the relative speed of the frames. So this gamma. And I'll write down E10, and then I'll have a speed of the frame, and I'll have P10x, which is minus P. So this I can replace with minus P0. So, and we already know the formula for that, and we know so it is nasty formula, but I don't have to kind of write it over here. And P, this guy, P1x. So where's the momentum of this guy over here? Well, that's going to be gamma u, and I'm going to get P10x. So, and of course I'm going to replace that with that plus u E10 for that, and other guys are 0. So this is how I got for particle 1, and I can get for particle 2. Okay, so this one dimension is very simple, and actually 2 dimensions is not that much more complicated, except there are more variables to keep track of, right? So that's the one we do next. you can already appreciate I did everything in the CM. That was very easy to do. And then I just use the Lorentz transformation because this thing is a 4 vector. I can memorize this Lorentz transformation. C equals to 1, very easy, all symmetric. Both are symmetric and C equals. When you put C equals to 1, then one of them has U and one over C, U over C squared. They all just becomes U. And the gamma is in front, and it's easy to remember. Okay. All right, let's try to do this nasty one too. Okay, so let's do the most general case. It's always going to be, when something's decays, it's going to be in a plane. So you can pick XY plane, you know, where all the action is happening. So you don't need to consider Z at all. All right, so we have two choices. We are going to do this with this or this with this. But this is the CM. We already know we should do that stuff in the CM. It's all simpler. And so a lot of the calculation would be, already we have gone through it. So we do this. And here I'm going to get, I use notations very similar to the one for one dimensional. So E10 for this particle plus energy for that particle should be equal to the rest mass, because this first particle is just sitting there, and C, it is actually mc square, and C equals to 1, so I just write m. Okay, so just write m. So all right, so this is just m. So this equation 1 I get, but in terms of momentum, they will have to be, because they're going to cancel. For momentum, we get P10 plus P20 equal to 0. That you can do more, and you can say that theta 10 has to be equals to pi minus theta 20. There's one consequence of this, and just call it one angle theta 0. So we just call this guy theta 0. We don't need to know both of the angles. Okay, so if I look at it, we have a actually the whole calculation, it will be almost identical to the one-dimensional calculation. So you can see I can go through it. So P10 vector equals to minus P20 vector, and that will means P10 magnitude equals to P20 magnitude, which I can just denote by P0. Okay, and so P10x, suppose I was looking at particle 1, okay, is just equal to P0 cosine theta 0, just using just one angle, so I don't have to write too many things. And I can have P10y is just going to be P0 sine theta 0. Okay, now that's all. We actually got pretty much everything. To get P0, we just look at this equation along with this equation. So we know that P01 is square plus M1 square equals to E10 square, and E20 square is P02 square plus M1 square, and these guys are equal to each other, p0 square plus m1 square and p0 square plus m2 square, and we just subtract it. Just a little bit different calculations, which is exactly same thing. So these guys will cancel out, and you get e10 square minus e20 square equals to m1 square minus m2 square. And so e10 minus e20 times e10 plus e20 equal m1 square. It's exactly same calculations. I'm not getting anything new, I'm just repeating it. So I can use 1. So this is equal to m, and then I can put m over here and then add and subtract. You can see e10 is going to be, and e20 similarly is going to be 2m m square minus m1 square plus m2 square, and 2m m square minus m2 square plus m1 square, like that. Okay, let me pause. Okay, so you can see that I am actually not getting anything that will give me theta 0. Just theta 0 is there as a free parameter. And what happens is, in center mass frame, when a particle decays, there is a complete symmetry in any direction. So in the center mass frame, you can see in the CM frame, say the particle is over here and it's at rest. Center mass is at rest. The whole thing is at rest. So you have complete symmetry, and the particle that comes out, the two particles can come in this direction. If one comes in that direction, then the other must come in that direction. And if one comes in, say one comes in that direction, then two must come in that direction. But it's completely symmetric. So this theta 0 is not determined, except that when you have to specify in CM, it came out at that angle. Or you can say I did the lab and I tell you what theta 1 is. Okay, so if it came out a particular theta 1, then I can say which way theta 10 have to be. Okay, so let me tell you the angles are related between the two. And so if you give me theta 1, then I can get theta 0. And let me tell you the angle relation now. Okay, so I looked up some formulas that we had derived before and cleaned up some of the things we have already obtained. So if you look at this, and if I were to kind of multiply top and bottom by E01, and this can be E01, E01, and upset C equals to 1, in all these formulas. So this just becomes E01, V01. It just P, this thing is same as P10, and so we got a P10, which is P0. Theta 10, I'm going to assign theta 0, and U E10, I mean, I multiply E10, not 01, 10. First is the particle, second is the frame, which I already know, and U is already known. It was moving with U, and we have a plus P0 cosine theta 0. So you can see, I can tell by using this which direction the first particle will come in the lab. And of course, you can also, using this and this, as you have seen before, we can write out what the E1 in this frame will be. E1 will be just gamma E10 plus u, that's the relative speed of the frames, P10x. And this P1 here, the x component, P1x, and then we'll have to get P1y also. It will be P1y, P10y, but this one will be gamma P10x plus u E10. So this is the beauty of using c equals to 1. The formulas look identical, okay? And I prefer that when I do relativistic calculation. So we have actually completed this calculation. It's been a really long video, and next is trying to do some electricity and magnetism using the idea that relativity is magnetism can be understood as a relativistic effect. Like in one frame you have charge is not moving, then you're going to have only electric field, and another frame which is moving with respect to the first frame, the charge will have its velocity and so will have magnetic field. So in your frame, if you're observing magnetic field, that means there is another frame I can jump to, where there will be no magnetic field in that situation. Okay. All right. We will stop here, and we'll talk to you later in another video. Just a reminder that you haven't subscribed, then subscribe please. Will helps the channel. If you like this kind of explanation, hit like button, and you can check out my website also. Bye bye.